Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today, before anything, I just want to remind you that your assignment 3 is due by the end of October 27th. Remember, the 8:30 rule is in play, so that means that you're welcome to submit if anything comes up or anything of that nature. You're welcome to submit after that deadline up until 8:30 in the morning, Regina time, to submit your assignment 3. So just like in the previous assignments, I allow you to submit overnight until 8:30 in the morning, just in case there's any technical issues or anything of that comes up. So just be aware of that. That's just like the other assignments. But yeah, this deadline is coming up. I recommend working on this if you haven't started. It isn't as long as the first 2 assignments, but don't put it off. So other than that, let's proceed to talking about context-free languages again. So I'm going to be wrapping up my discussion of context-free languages in this lecture. And anything I talk about after this point might touch back on context-free languages, but we're going to be kind of working our way up even further, where we might bring in some more discussion about context-free languages at some point in the future. Well, I'm not quite sure. We'll see where we go from here. But I first wanted to talk a bit about the equivalency between pushdown automata and context-free grammars. So we already know that a language is context-free if there exists a context-free grammar that I can use to generate that language. So I could generate any string of that language. We say that that language is context-free, right? Well, you can prove that if a language is context-free, then most certainly there's a pushdown automaton for it, and vice versa. So if you think about it, then that means that for every one of our context-free languages, there's a pushdown automaton, but also there is a context-free grammar. Now, if you're wondering how exactly you can go about this, there's a couple different proofs out there. I'm not going to be showing you this proof because we only have so much time this term. If not, I would happily show it to you. But it takes time to set it up. It goes like this. So imagine I give you a context-free grammar. There's a way to convert a context-free grammar into a PDA where it accepts by empty stack. So remember the other day I mentioned that there is this other notion of acceptance with a PDA, which accepts when the stack is empty. This is not the way that we've been talking about it, but it is another equivalent way of talking about acceptance. However, you have to design the PDA ever so slightly differently. So once you're in that stage, what you do is there is an equivalency between the PDA that accepts by empty stack and the PDA that accepts by final state. So this is the one that we have been talking about, by final state. So you can go between them, and also you can kind of go back and forth between them. So this is the picture for which you could prove the equivalency between context-free grammars and PDAs that accept by final state. There's this intermediate step here. So this is one way you can go about it. So the construction works like this, kind of like when we talked about Claney's theorem. There was that connection that we had between them, converting between one finite automaton to another, or from regular expression to a finite automaton. This is the picture for context-free languages. So this is just generally the idea of how it works. I'm not going to go into the details about this, but you could find details about this specific proof in the Hopcroft book, the one I call HMU. But I will not ask you about this at all, because we just don't have time to talk about it. Like I said, there's a lot of fun, juicy theory around these things. So just the big summary here is that both PDAs and context-free grammars describe context-free languages. That's the big thing I need you to know about, is that for any context-free language, there's going to be a PDA, and there's also going to be a context-free grammar, and it does, in fact, exist a way you can convert between them. So just be aware of these 2 facts. So that being said, I want to talk now about properties of context-free languages. There's so many things I could talk about with context-free languages. Some I'm able to highlight here. Others like I said, we'll never get to the juicy bits of this class beyond this if I keep talking about context-free languages. I would happily do so, but it's just not enough time. So the first one I want to talk about is that there actually do exist languages that are not context-free. So just for an example, Here are 3 different examples of languages that are not context-free. They also could be quite surprisingly simple. Just for example, here I have a to the n, b to the n, c to the n, where n is greater or equal to 1. It could also be n is greater or equal to 0. It doesn't make much of a difference. This looks awfully a lot like remember when I showed you when a language wasn't regular? I just had a to the n, b to the n, or 0 to the n, 1 to the n. Notice that all I needed is just one other symbol, and that's all of a sudden now we're pushing past what a context-free language will be. And you might ask, Dan, how do you prove that these are not context-free? Well, there exists a pumping lemma for context-free languages, and its setup is quite similar to the pumping lemma for regular languages. So if you find yourself morbidly curious about doing this, or even wanting to pursue this further, you're welcome to read Chapter 7.2 of Hopcroft or 2.3 of Sipser. They both talk about this in good detail. The Hopcroft one especially. I won't be examining you on your understanding of using this pumping lemma, but if you're curious, just feel free to explore this. Just to give you a general flavor for what this is like, remember in the pumping lemma for regular languages, we know that for every string of a sufficient length, there's a way to divide the string into 3 parts. There's an x, y, and z part. And then what we had properties that these 3 parts exactly had, so that I could talk about them with respect to the language. So we had this idea that I could keep repeatedly pumping, which corresponded to a cycle in the graph. Well, not the graph, the finite automaton, which is represented as a graph. But there's very much a similar analog over here, where instead of it being 3 parts, there's 5 parts. Yeah, it gets more fun like that. And it corresponds to parse trees. So where we before had like a DFA, this was going to correspond to talking more about parse trees and how those parts relate when it comes to the parse tree. So I just wanted to mention that, and I just wanted to give you a flavor of what kind of languages are not context-free. So just having 3 different symbols where they all are equal to one another is not context-free. Likewise, even if I make it so that they vary by certain amounts, this is also not context-free. And even, believe it or not, if I give you the same string twice in a row, that is also not context-free. However, you might recognize this example. Well, this looks very similar to something else I've shown you before. I've shown you W with W reversal, right? We know that one's context-free, right? However, just if I ask the string and then I want the string again, that is not context-free, which is quite surprising. All it is one little simple tweak, and boom, now you're not dealing with something that's context-free anymore. So just be aware of this is that there exists some of these languages that are not context-free. So for some of you, you might be looking at some of these and like, okay, well, that kind of makes sense, seeing as we have a stack, and the stack is only capable of storing so many things like a primitive form of memory, right? So for some of you, this might click quite nicely. Others, I want you to think a little bit about it. If you find yourself compelled to look at the pumping lemma for context-free languages, I encourage it, but I'm not going to require it. So are there any questions about that? So just be aware that there do exist languages that are not context-free. And all of these can be proven using contradiction with this pumping lemma for context-free languages. But knowing at least these basic patterns is enough to really see where you need to go with this. So question. We learned about regular languages. Then we learned context-free grammars cover a broader family of languages, contain regular ones. Is there a category for covering part of a bigger category of languages? Yes. Yeah, that's exactly where we're going to be going from here. So you're going to see that since I've told you that there exists languages that are not context-free, there's naturally going to be some other superset of language that's going to consist of languages that's going to subsume all the context-free ones. So good catching on that. Wonderful, wonderful. So you're going to see that all of these languages are going to stack on top of each other, and they're going to form a hierarchy. So it's going to be kind of neat. So that's really all I have to say about the first part of this. So just be aware that these exist, and there is an actual pumping lemma for context-free languages you can use to establish these facts. So now I want to move on to talking about closure properties, those good old closure properties. And some of this actually connects to the example I gave you to read Last day. Believe it or not. So I just want you to keep in mind those three examples. And I want to talk about closure properties. So just recall what I'm going to be talking about here are if I give you some context-free languages and I perform some operation to them, I would like to know whether they're going to be still context-free or not. So it's closed. That means that it's going to remain context-free. So context-free languages are closed under the following operations. So at first you're going to say, oh, Dan, you're going to like list everything we had last time with regular languages. And this is going to be the weird twist for this, is unfortunately that's not going to be true. It gets not as fun as you might think it might be. Be like, oh, I have all these lovely properties. You're going to have some lovely properties, but some that aren't. Just to make this extra fun, I'm going to wear my fun hat. Let me put this hat on. There we go. There we go. Wonderful. Wonderful. Because I'm going to be exploring some closure properties. So let's proceed. So the first one is union. So we do get union. So if I give you two context-free languages, say I call them L and M, then you know that L union M is closed. So meaning that if I give you L, it's a context-free language, M is a context-free language, that will be resulting in a context-free language. Now, if you want a sketch of the proof, so here's a nice simple way of approaching this. Now, this should remind you a little bit of the example I showed you or got you to read last time. This should remind you a little bit of that. So here's a sketch of how you could do this. And all of mine are going to look very similar to this sketch after each one of these. So as L and M are context-free, there are context-free grammars, G1 and G2, so that L is equal to the language of grammar 1, and M is equal, for some reason I'm compelled to write L again. It's M is equal to the language of context-free grammar G2. So that's just us using the definition of context-free. So now what I'm going to do is I'm going to build some super grammar that's going to construct this union process. Now, the wonderful intuition we have with context-free grammars is I have that bar, that notation I use for bars when I have multiple production rules with the same head. I always called it OR. And there was a very good reason why I called it OR. It's like picking an option. We're going to take advantage of that fact. So create a new context-free grammar. What a Monday, man. This is fun. Create a new context-free grammar for L union M by taking the symbols and production rules together of G1 and G2. Now I'm going to let S1 and S2 be the start symbols. I'm going to let them be their start symbols. So when I made their symbols, I mean S1 is start symbol for G1, S2 is the start symbol for G2. Then add a new start symbol. S and add production rule. Add production rule. And I'm going to give us the first one, and you're going to help me do these other operations. So, but here's the production rule. S is going to produce S1 or S2. Isn't that neat? So this is the start symbol for the first context-free grammar, G1. This is the start symbol for G2. So all I have to do is just pick one or the other, right? And this will allow me to generate a string respectively from each of the two languages. Does everybody see that? Is that kind of cool? So I just, with a very simple tweak of the finger, I can get myself union. Okay, so the next one I want to talk about is concatenation. So concatenation. So that means, of course, that L concatenation M, just as a reminder, or just LM. The proof sketch goes like this. It's really, like, once you see the first sketch, it's really easy to see what you might do here. So we're going to use the same setup. Same setup as above. So we're going to use the same setup as above, except for one thing. Instead of changing and adding this production rule, what we're going to do instead is add a different production rule for the beginning. Except for the new production rule being, so imagine I give you S. So does anybody have any ideas of what I could put here if S1 is the start symbol for G1 and S2 is the start symbol for G2? What should the production rule look like if I want to get concatenation? Yeah, it's literally just S1, S2 like this. That's it. It's that cool. Yeah, exactly. That's all I have to do, believe it or not. So instead of adding this rule, you're going to just add that one. It's really simple. So now you might naturally ask, if I give you, and I tell you that star also is closed, so I can again use the same idea. So if I give you L star, that's indeed closed. So the proof sketch for this one, again, it should feel quite natural what you might try. So same idea as above. So it's the same setup, except we're going to add the production rule. So of course we're going to have S, right? So we're going to have S, that's our new start symbol. And now remember, star is supposed to take in no occurrences of it, and then any number after that, so 0 or more. So what would it look like if I want to put it in a production rule in for if I wanted 0 occurrences? Well, that corresponds to what? What should it correspond to? Yeah, epsilon. Yeah, so it's epsilon, so that's your 0 times you include it. And now the great part about this is if I want to include more, I could just use this strategy I used much earlier on, where I have the start symbol for G1, and then I just put S right there. So I could just keep repeatedly doing this over and over again. And then epsilon I'll use both as the ability to accept the empty string, but also, sorry, not accept, generate the empty string. I should be very careful with my language. Or it allows me to introduce another S1, and I can keep repeating this as many times as I'd like. Is that kind of cool? So this is how we could get union, concatenation, and star just by making small little tweaks to the context-free grammars. So we just lump them into a bucket, and then you just add this in. And this should look very intuitive to you if you think about it. Like, well, the first one, this should remind you a little bit of what I did with that PDA in that example I asked you to read. This should remind you a little bit of that, where I made an epsilon move. This should remind you a little bit of that. So one other operation that's actually closed as well, I'm not going to give you the proof for it, but the proof is quite natural. You basically flip all the parts, the right parts onto the left parts of the production rules. Reversal also is in fact closed for context-free languages. So if you just apply reversal to a context-free language, it stays a context-free language. So those are all the ones I wanted to talk about when it comes to closed properties. So are there any questions about these? Or do you think this is kind of cool? It is kind of neat. So that's the good news, is we have all of these. The bad news, however, is that we lose some. We lose some of our favorites. And I want you to keep in mind the 3 examples that I had shown you that are not context-free. The ones I just had here on the board a moment ago. Because I'm going to show you some counter examples, because that's normally what you would do, right? If I want to tell you that, oh yeah, no, the language is not closed, it's not context-free, there better exist a counter example that actually shows that. So, however, unlike regular languages, some operations are not closed. Some operations are not closed. So just be aware of that. That's very important. So don't just assume that all of them, you get all these operations for free. You have to be very careful. The first one is intersection. So you don't get intersection. That's not a guaranteed case. Now, I wanna give you an example. So suppose I have L1. So here's just a counter example of where, well, this is an example for which you're going to find the closure is not going to work. So suppose I have a to the n, b to the n, c to the i, where n is greater or equal to 1 and I is greater or equal to 1. So you're going to have it where these first 2 letters, the a's and the b's have to be of equal quantity, but c could be whatever you like as long as it's positive. So, question for you. Is this a context-free language? This one most certainly is. It is. You can design a context-free grammar for it, but you can also actually design a pushdown automata for this one. This is actually exactly the example, one of the examples that I gave you actually in the notes for you to read. This is exactly that one of those two. It's just it's cloaked in other notation. So you might ask how? Just take a look in the notes. There's a PDA there because I used 2 PDAs that I performed a union on the 2, if you think about it from what I did over there. But yeah, so this is an example. This is indeed context-free. So this is a context-free language. How about L2? Here's L2. I'm going to allow the first one to be whatever. Then I'm going to have the last 2. I'm going to allow the last 2 to be, in fact, equal. Now, I don't think I've shown you exactly this one, but I must stress that this one also is context-free, this language. I'll let you convince yourself of this fact. Now, when I take L1 intersect L2, now it's kind of hard to really see what the result of this should be, but I want you to think about it. Okay, this one consists of strings for which the A parts and the B parts are equal, and C is allowed to be whatever as long as it's some positive number of C's. This one, the number of B's and C's have to be equal, but the A's are allowed to be whatever as long as it's a positive number of them. If I want to get the two sets of strings, the two languages that have only the strings that are in common amongst these two, notice that this first one says that the number of A's has to be equal to the number of B's, and this one says that the number of B's has to be equal to the number of C's, right? But notice if I want the ones that are from common amongst both, I know that for sure that the number of A's most certainly has to be equal to the number of B's, right? So it means that it's going to look something at least like the following. So I'm going to have at least A to the n, B to the n, right? And if I look at this side, notice that if I want strings that are common amongst these two, I know that the number of C's has to be equal to the number of B's. So that means that I'm going to have to drop this allowing to be whatever it wants to be. So notice that that's also going to end up being C to the n, which n is greater or equal to 1. And now I want you to remind yourself of something earlier this lecture. Is this context free? What? No, that one is not context free. Exactly. So this is not context free. This is not a context free language. So there's a simple counter example. If somebody told you one day, hey, look, all context free languages are closed under intersection, you could present them this very simple counter example. So another one is complement. Unfortunately, we do not get complement. So I'm talking about L bar. So I put an example in the notes for this one. I'll ask you to take a look at it. So I put a pretty basic example, but essentially what happens is you end up getting it where if you get the complement of the third language, so if you take the complement of the language which had WW, if you take the complement of that, you can design a context-free grammar. And naturally, because the original one has a context-free grammar, but I know that when I just have WW, that is not context-free, then most certainly complement will not be closed. Another one is set difference. Unfortunately, we do not get set difference. Set difference we do not get. Now, you might think to yourself, Dan, why would we not get set difference? Well, remember, set difference can be defined in terms of intersection and complement, right? That's why we don't get difference. So it just sort of comes as a consequence of these two. So surely you can't intersect a complementary language and expect it to still be to close. Does everybody get that? So remember, set difference, if I give you that's what set difference equals, right? So most certainly you have an intersection here and you still have a complement here. So you most certainly are not going to be able to get a closed language. It's not going to stay context-free, possibly, as a general rule, right? So I'm just saying that you can't guarantee that it's closed all the time. So here's a third thing I want to talk about. So this is an interesting side note. So here's some interesting closure properties. For CFLs with regular languages. For regular languages. So you might think to yourself, Dan, some of these operations were not closed for if I give you two context-free languages. What happens if you take a context-free language and you try to do stuff with a context-free grammar? Because remember, not a context-free grammar, a regular language. What am I saying? A regular language. Sorry, I'm getting really excited about showing you this. So if I give you a regular language and a context-free language, now remember, every regular language is in fact context-free, right? So this shouldn't be too weird. It's just that I have a regular language and a context-free language. I would like to see if any of these operations are they closed. So, so question, what if we put complement on a non-context-free language? Do we get a context-free language? Is there a chance for that? Actually, the example I mentioned here, where you have, the one I'm referring to is where you have WW, such that W is some binary string. If you take the this isn't context free. However, its complement is. Its complement is. Like I said, just take a look at the example I'm going to have in the notes. It shows you an example exactly what you're saying. So I want to talk about just some interesting things you could do with this. So if R is a regular language, and L is a context-free language, I want to point out for you that one, the intersection of a context-free language and a regular language is a context-free language. So you do get the closure property, but it's not quite exactly what you wanted. It's not two context-free languages. Instead, you have to if you take it with a regular language, then you most certainly will get a context-free language. Now, you might ask, Dan, how do we guarantee this property? Now, I'm not going to show you the proof, but I want to give you the idea of this proof, because it is very fascinating in its own right. But like I said, there's only so much time that I have with you for this term. So I want to give you an idea. So here it is. So the whole idea is that you take a PDA. So you have a PDA for L. So there's a PDA for L. And then you can have your DFA for the regular language. So you have some DFA. It could be whatever. It could be a DFA. And that's for language R. And what you do is you essentially take these two together and you simulate them in parallel. So you simulate them in parallel. The way you do this is you take the Cartesian product of the states of the DFA and the states of the PDA. And remember, a DFA only consists of states and transitions, right? Well, you can think of it like this. Well, the PDA also has states, but it also has the stack, right? So what you do is you take the states of the PDA and the states of the DFA, you take the Cartesian product of these two things, then you have a unique way of talking about each state of the DFA and of the PDA. So there's a nice construction that does exist. It's in the Hopcroft book if you're curious about it. And what it does is it effectively simulates them in parallel by generalizing over both of them, by using the Cartesian product to encode the instantaneous description of the PDA that also encodes the DFA within it. That's kind of wild. But yeah, so that's how you could prove that this intersection operation yields a context-free language. Now, you might ask, okay, well, what about set difference? Well, yeah, you get that. So you have L set, you take L minus R. This is a context-free language. Now, you might ask, Dan, how do you know that? Well, look at this. Remember, this is the set difference right here. So remember, M is just R here. So remember, the complement of a regular language is still regular, right? And I just established for you, or at least gave you the idea of how you'd prove that the intersection of a context-free language and a regular language is in fact context-free. So I'll end up with a regular language intersects with a context-free language, which yields a context-free language because of this first one. So it's kind of slick, right? So if you find yourself curious about this, like, oh, I have some regular language and I have a context-free language, there is a way that you can in fact still maintain these closure properties. So that brings me to talking about decision properties that context-free languages have. So this is where things are going to get a little bit open-ended. So there's some things I'm going to just touch upon. Other ones I'm going to go a little deeper, okay? Because like I said, I could easily, like, there are classes that do exist out there where all they do is talk about one of these classes of languages. And my job is to kind of walk you through on a little journey through these to give you just a peek at each one as we build up, highlighting some of the more important aspects of them, so that we can ultimately get to an idea of, like, what is computation? That's kind of where we're working our way up to. We're almost actually at that point, believe it or not, which is kind of wild. So let's talk about decision properties. So I did the same sort of deal with regular languages. That time I went a little bit deeper. This time I'm going to leave things more open-ended. So decision properties of context-free languages. The first thing you should know is that there do exist algorithms for testing if a context-free language is empty. So remember, we talked about the emptiness of a language before. And if a context-free language is finite. So if you're wondering what the flavor of these two things are, they actually both closely relate to a lot of the theory that we've seen when we were converting context-free grammars to Chomsky normal form. So if you're wondering, there are so-called reachable symbols in a context-free grammar. And often the goal is that we would like to show that there exists some terminal string. Like when we had our parse trees, we would like to have it where I can guarantee you that there's at least one terminal string, or epsilon. So what you could do is you could take one of the steps that I showed you with the Chomsky normal form conversion. There is a way you could take that. If you're curious more about this, it's in the Hopcroft book, if you find yourself curious about it. There is a way to modify one of those steps so that you can generate so-called useless symbols versus non-useless symbols. And it has this reachability process. It's quite similar to the way that I did it actually with the regular languages. So what you do is you could build one of these and you could just say, hey, look, is it empty or is it not? It just depends if there exists one terminal string or epsilon. That's all you need. Now, when it comes to checking finiteness, a very similar process is used as well. It's not quite exactly the same, but it's very similar. You actually can build a graph. You could check for cycles. So this is actually something that I had mentioned actually when we talked about regular languages. There's another construction like that where you could build a directed graph and then you could check for if there exists a cycle on variables that exist in the context-free grammar. It's a process that's very similar. That's why I'm not highlighting them here right now. Is that they're very similar. So now, the next thing I want to talk about is testing membership, because this is something that was brought up. A student had asked me about this during class, is how we test if a string is in a language. In this case, we're interested in context-free languages. Now, for regular languages, it's really straightforward, right? I could just use a DFA and I could just check it, right? It's really intuitive. With the context-free languages, it's not so much. It's a little bit trickier now. So the first thing I want to do is I'm just going to assume that I'm going to let the length of a string w be equal to n. And I must stress that there's many different ways you could test membership of a string in a context-free language. Many different ways you could do it. But I warn you, most of them are very inefficient. I mean, like exponential running times. So many inefficient in n, just to be clear, taking exponential time. Algorithms. exist depending on representation. Depending on the representation. So I'm talking about a context-free grammar versus a PDA. And as I established earlier, the difference, like from a theoretical standpoint, it doesn't make a big difference. It only depends on how efficient you want your algorithm to be. Because remember, whenever there's a context-free grammar, there does exist a PDA. So just be aware of that fact. So you're going to find very often I'm not going to talk about, oh, for a PDA you do this. If it's a context-free grammar, do this. I'll just assume that there is some way to transform it into the other one. So this is the neat thing. And somebody asked me, like when we're talking about Chomsky normal form, why would we want to use this thing? Well, I'm going to show you now why it's very useful. Because I wanted to hold off on this a little bit. And it comes back to something I mentioned when I talked about Chomsky normal forms. So I'm going to describe one inefficient process for doing this, and I'm going to tell you a much faster way of doing it. So watch this. So, however, for some context-free grammar, which we can obtain from converting a PDA, if should we need it, obviously. Now, for the sake of this discussion, I'm going to assume that the size of the context-free grammar, that means all the symbols used to represent it, is of some constant size. Whenever I describe a running time to you, if you wanted to include this in there, it actually is technically part of the input, so you'd have to multiplicatively include it with the running time. Just as I mentioned. I'll mention it more explicitly when we get there. Where we treat its size as a constant independent of W. And as I mentioned, remember, the context-free grammar might be really big. That's why I'm trying to keep it separate from W. We have a couple of approaches. So the first one, actually both of them are going to relate to Chomsky normal form. So CFGs in Chomsky normal form, have the property, let me just switch my marker. I've had enough of this marker. It's gone. It's gone. Here we go. Let's go. We have the following property. Have the property that their parse tree, I don't think this marker is that much different, that their parse tree, now, what did I tell you about the structure of this parse tree? What did I tell you? What kind of tree was it? What kind of tree was the parse tree? It's binary, exactly. That the parse tree is binary, and something that you could actually prove using induction. And is the following, watch this, and the number of nodes labeled with variables will equal 2n minus 1. So it's going to be, so whenever I give you a parse tree and you ask me, hey, look, I want to generate some string. So if I arbitrarily apply the production rules for my CFG in Chomsky normal form, if I count up the number of internal nodes, so those are the ones that are going to have variables sitting at them, the number of them is going to be exactly equal to 2n minus 1, which is kind of fun, right? That's a very nice property. So here's what you could do. So it's very, very neat, is you could do the following. you could just simply try listing all the parse trees. I didn't say this was going to be efficient, by the way. All the parse trees, and see if one yields. So remember, that's why I'm talking about the terminal string. It yields W. So this is, of course, going to take exponential time. Exponential time in n. So this is not a very fast process, but you can do it, and it's a bit better. We're doing a bit better. Now, the other way you could do this, and I'm going to just move over to the other board. So that's one way you could do this. So the Chomsky normal form does give you a nice structure for which you can enumerate all possible binary trees. Or what you do is you check all possible orderings of those variables for which they get applied in the context-free grammar. So it's a bit, so you could use backtracking, for example. That's a nice way of approaching this, is you can use backtracking. So if you really just don't want to do an absolute brute force search, you can use backtracking. But believe it or not, you can do much better. You can actually do much, much better than that. You can do much better. There, as I alluded to, I may mention this at some point. So if you give me, so given a context-free grammar in Chomsky normal form, so I'm going to assume you give me some context-free grammar. I'm having a good time with everybody. Just know that I'm just playing, okay? So given a context-free grammar in Chomsky normal form, given a context-free grammar in Chomsky normal form, it can be provided as input to an algorithm called the CYK algorithm. You wonder what the CY and K stand for? They stand for the who are often attributed for the discovery or invention of this algorithm, depending on how you like to view things. Now, if you're wondering what technique this uses, it uses dynamic programming, which employs dynamic programming. It's bottom up, by the way, if you find yourself curious about it. I usually like to think of dynamic programming as bottom up, typically, but it's this is through tabulation. Some people like to call this a table filling algorithm. So it's tabulation bottom up. So it's a bottom up process. I'm going to say it runs in big O of n cubed time. If you're wondering where the size of the grammar pops up in this algorithm, it would be the size of the grammar times n cubed. But yeah, this is much better, right? This is much, much better. So if you get your context-free grammar in Chomsky normal form, you can give this as input to the CYK algorithm. And that will be able to tell you if W is in the language or not. So one thing, I'm just going to touch upon this. Is it okay if I take 1 or 2 more minutes from you? I want to just drop a few bombshells on you. And then we're going to end it for today, and then we'll be moving on to a new topic. Is that okay? Just give me a thumbs up if we're okay with going for another minute. Okay, so let me just wrap this up. So unfortunately, so far we have a lot of neat properties. But unfortunately, there do not exist algorithms to do the following. So remember, I told you in a previous lecture that there is no algorithm that I can use if I give you some context-free grammar that it'll tell me if it's ambiguous or not, right? So you could do even worse. It gets even worse than that. So let me give you a few examples of things that, that will make me weep in my sleep. I'm telling you, I'm going to do this later, okay? So I'm really going to do it. So are two context-free languages equal? Notice I never addressed equality of languages. There is no algorithm for that. Art. So that's the first one. I'm coming out strong, okay? So is a context-free language inherently ambiguous? So remember, this just simply means that there is no context-free grammar for it that is unambiguous. So it means I'm not even just telling you, okay, here's one context-free grammar, tell me if it's ambiguous or not. I'm asking, is there just some general process that if I give you a context-free language, can you tell me if it even has an unambiguous grammar? And unfortunately, the answer is no. This is a generalization of the one I showed you the other day. So obviously if I give you for one context-free grammar, I can most certainly test if it's ambiguous or not. So if I had some process I can use to test this thing, then most certainly I could solve this problem. But the problem is that this is much more broader, right? So now this is going to be a little bit of a stranger one. Is a given context-free language L equal to sigma star? Where sigma is its alphabet. All of these do not have algorithms. Like I said, this is where things start getting a little bit funny. So that being said, I'm going to stop right here. When we come back, we're going to start talking about Turing machines. So we're going to be moving up one rung on the hierarchy of languages that we're exploring. See, fun hat. It's the fun hat that makes this work. So when we come back, we'll start exploring that. I want to say thank you very much and have yourself a beautiful day. I'll see you later.